Okay, everybody, I'm gonna officially start. Uh, this is so weird, giving a lecture live on YouTube. So I thought, since we're breaking new ground here, this could be the first time in my life that I've ever given a public lecture drinking a beer. So let me start off by introducing myself. My name is Bob Abraham, and I'm a professor of astronomy and astrophysics at the University of Toronto. And I love giving these kinds of talks. And the reason for that is because I feel just unbelievably grateful for the way that I can basically do as a profession the sort of thing that I've wanted to do ever since I was like a 12-year-old kid. And the reason that that is possible is really because of you people. At times like this, when we're faced by turbulence, and you see the way the fabric of society has to kind of come together. It makes me realize how important it is that we all try and pull together. And I wish I could do more. I wish I could do more at this time to help. There are so many people out there that are working so hard to try and help us get through this kind of thing. And and so this is basically the best I could come up with to try and give a little something back, to try and basically say thank you for enabling me to do this kind of thing. So really, when you stop and look at it, though, what can people like me contribute? Because I'm not a medical professional. I'm not an epidemiologist. Even at the best of times, I'm not able to help your car go further on a tank of gas, or help your microwave be 20% more efficient. So those aren't the sorts of things that I can contribute, but I do think I can contribute something, and that is giving people perspective. Okay, a perspective on how their lives are basically impacted by the universe, and how they in turn impact the universe. So this is sort of the cosmic perspective on life, and that's what I'm hoping to basically touch on with this talk. Okay, is to basically kind of ground you in terms of where you are in the universe, both in time and in space. So without further ado, let's try and do that. So let me share my screen. And start this thing off. Okay, so the talk is entitled Finding Your Place in Time and Space. So let's start off with your place in time. So a magnificent thing that has happened over the course of my lifetime, even over the course of my professional lifetime, is we've gone from being ignoramuses about basic things like the age of the universe to knowing the age of the universe to a few percent. Even on days where we're less cautious, to a fraction of a percent. So that is spectacular progress. So I can sit here, world of YouTube, and tell you that the universe is 13.8 billion years old, plus or minus a tiny amount. So 13.8 billion is a pretty big number. And I personally, I don't know about you, but I personally find it really difficult to wrap my head around big numbers. Can't really relate to them. 13.8 billion of anything is hard for me to grasp. So what do you do? Okay, so I'll tell you what I do. Basically, I cheat. Whenever I have difficulty coming up with a way to handle these big numbers, I try and come up with a tool, okay, that lets me deal with this stuff without having to deal with the math. And not being very original, I just stole my tool or my trick from my hero, Carl Sagan, who came up with this concept called the cosmic calendar. So what Carl Sagan said was, okay, look, here's what we're going to do. We're going to stretch the entire history of the cosmos. It's 13.8 billion years that people can't wrap their heads around. And instead of 13.8 billion years, instead, what we're going to do is we're going to compress that so that the calendar year represents 13.8 billion years. So Carl Sagan didn't actually know 13.8 billion years because he sadly died before the spectacular progress that I'm describing. But that's the idea, okay, is that we compress the whole of the history of the universe into one calendar year. So the Big Bang, the creation of the universe, occurred at the moment of New Year's 1 year ago, January 1st. And here we are at the very end of that year, just turning over into a new year, December 31st. That's the whole history of the universe. So if you play this game, it's actually kind of interesting because it lets you kind of more easily conceptualize when key events occurred in the history of the universe. So, one key event is in May, our Milky Way galaxy was born. So I'm going to not assume that you know what the Milky Way galaxy looks like in any detail, other than to know that it's a collection of stars that we are part of, and I'll describe in greater detail later. But it's basically the key collection of stars that formed about halfway through the calendar year. But of course, the star that we should all have as our favorite star is the sun. And the sun formed in September, and that's when the Earth formed too. Okay, so right around September 3rd is when the Earth formed. And the two formed together because, of course, the Earth formed from the material left over from forming the star that is our sun. So those two are linked. All of what I've just described actually, again, represents spectacular progress. We now know way more, for reasons that I'll describe in a while, about how things like stars and galaxies form than we did when I was that 12-year-old kid just getting into astronomy. Just spectacular progress, but there's so much left to know. It's unbelievable. And I think one of the most important and enduring questions, and I think arguably the most interesting and important question of all, is, are we alone? Are we alone, in the universe? And that's something where, over the course of my lifetime, I don't think we've made very much progress at all. So I can't tell you whether we're alone or not, but I can tell you some stuff, which is that, at least in the case of our own sun, when we formed in September, Earth congealed, from the material left over from forming the sun in September. It didn't take much time at all for first life to emerge on Earth. So the planet formed around September 3rd, and first life appeared on Earth on September 22nd. And that must be telling us something. But what beyond the basic fact that as soon as life could appear on our planet, it did appear, does it tell you? So I don't know. Okay, but another interesting fact is that although life emerged almost as soon as it could emerge, just as soon as the Earth stopped glowing, basically life sprung on this planet. It remained incredibly simple. Okay, it was just basically, cyanobacteria, simple organisms, single cell organisms for just the longest time. Okay, so here we are in September, and the oldest fossils, these bacteria, date back to around October. Um, uh, Reproduction in familiar forms, like through sex, evolved slowly, something in like November. But then it took the month of December for things to really kind of get interesting. So let's look at what happened in December. Let's zoom in on December. Okay, so interestingly, the primordial atmosphere of our planet didn't have very much oxygen at all. And so, when we talk about the cosmic perspective, one aspect of the cosmic perspective is that there's this deep relationship between life and the uh, atmosphere of the planet. And so why am I emphasizing that? Well, it's because we're living in this time when there's this, skepticism that, activity of people could have anything to do with, the temperature of the atmosphere. And I find that, I don't want to get too political, but I find that surprising that people are shocked that that could happen, because, there's this close relationship between life and the properties of our atmosphere that stretches back, almost to the beginning of December, because the oxygen that we're breathing all emerged as the product of life. That cyanobacteria that I was describing earlier, those biological processes are what put the oxygen in the atmosphere in the first place. So there's a close relationship between life and our atmosphere that dates back to the very beginning. And the other thing that people seem to have difficulty wrapping their head around is the prospect of change. We've seen over the course of the last few weeks how our society can turn on a dime and be upended. Well, on a larger scale, those sorts of things can happen to planets as well. All right. So if you look back to the beginning of December, around December 5, for example, Mars, which presently is this desiccated wasteland, Mars was this, beautiful paradise, right? It had a relatively thick atmosphere. It had flowing liquid water on its surface. It was, cosmically speaking, kind of a paradise. And yet somehow from December 5 to where we are today on December 31st, Mars has just died. It's turned into this desiccated wasteland. Why that is would make a fascinating talk on its own, I think, but we'll just leave it for now. Okay, so then let's move on. Okay, December 16 is a pretty big day, okay, because right around then something happened that took the incredibly simple life that we're familiar with in the form of cyanobacteria, and somehow turned the dial on complexity. And that dial, the complexity of life dial, actually got turned to 11 on December 17th at a time known as the Cambrian explosion. So that's another thing that I think is worth wrapping your head around. We talk about living in an era where species are disappearing, and asking ourselves whether or not we might be having an impact on diversity. And there's this sense, because of course we live today, there's this sense that today must be this incredibly special time, because we have this kind of vision for evolution that is a model where things keep increasing in complexity and sophistication, And so we think that life today must have been the most sophisticated life ever was. And in some ways, I suppose that is true. But in terms of biodiversity, that is certainly not true. Okay, so this process by which life advances and then regresses uh, is a process that is connected with events in the universe, as we'll talk about in a moment, and which in some ways reached its peak in mid-December. So, hundreds of millions of years before we were on the scene. Uh, this Cambrian explosion was life's greatest experiment in diversity. So that came and that went, and I'll show you some examples in a moment because I think that they're just amazing. But December 24th rolls along, and then we reach what my kids at least think is the apex of life, where dinosaurs appear, and the dinosaurs have actually a pretty good run. Okay, so they basically turn up on Christmas Eve, and they stick around until December 28th, but then they disappear, and we all know why. Okay. Uh, Another thing that's happened over the course of my life is that, it's become clear that the main driver for the extinction of the dinosaurs was a cosmic event, a strike by a meteor or a comet or an asteroid that wiped them out. So there's a intimate connection between events in the history of the universe and life. And that's just one amongst many examples for what's been happening throughout the whole of December. So let's take a look then at the sorts of things that were around at the time of the Cambrian explosion. So right now, it's fair to say that most life is basically operating on the basis of certain magic numbers, right? So, one magic number is 2. We have binocular vision. We have 2 eyes. Another magic number is 5, right? I've got 1 head. I've got 2 hands, 2 legs. So that basic form for life, is one that's pretty familiar. You can look at, your dog. It's based on 2 and 5. You can even look at things like starfish, which are based on 5. And that number is something that actually was not, just handed down. It's something that sort of emerged, but at the time of the Cambrian explosion, that number wasn't set. Okay, so the creatures that you can see, living at this time were so extraordinarily weird. They bear essentially no resemblance to anything alive today. So you can look at, for example, one striking instance, which is Opabina regalis. So this is a creature. It's about 10 centimeters long, which had a nozzle-like trunk, which had spiny jaws at the end of its trunk. It had gills that act a little like wings. This is totally unrelated to anything that exists today. You can, take it to a even, greater extent, and you can look at Anomalocaris canadensis. So rather than being few centimeters long, this thing is about as big as you or me. So it's about 6 feet long. So this thing was like a shark swimming around in the Precambrian seas. It had razor sharp teeth that were arranged kind of in a scissor-like fashion in a circular sort of mouth with shrimp-like appendages. So if you could imagine that thing swimming behind you, grasping you in those little shrimp-like claws with their razor-sharp teeth, and then funneling you into its mouth. That's the sort of thing that we had to deal with then. But there's nothing like this now, nothing at all like this now. And so the question is, why not? Okay, so what happened? Why are we, living with, these magic numbers of 2 and 5? Why is it that we, for example, don't have 14 legs, like hallucigenia. Why don't we have, mushroom-like heads? Why don't we have, walk around with these, huge spines, sticking out of our backs? Um, and the answer is nobody knows. But one good bet is that it's simply contingency. Okay, it's the way the universe operates with this intimate connection between planets and the cosmos. Events like these, periodic mass extinctions, which are driven by asteroid impacts, essentially add sort of a roll of the dice that every once in a while just basically freeze out some magic numbers. So, if this asteroid had hit somewhere else, maybe the prevalence of a particular species would then change, and then ultimately it would lead to the next phase of life, and that number would then change. So we have this super close connection between life and the history of the universe. Maybe if that meteor had hit on a Thursday instead of a Tuesday, we would all be dinosaurs right now rather than mammals. So, okay. So that, asteroid did hit when it did hit, and it, led to, the rise of the mammals. And those mammals, which started off as little marsupial-like things, did evolve into things that look like apes and then ultimately people. But all of this, happened late. And so it's appropriate to just focus our attention on just the last day of the cosmic calendar. So let's look at this thing. Okay, so around 1:30 p.m. on the last day of the cosmic year is the origin of Proconsul and Ramapithecus, our nearest ancestors amongst the apes, or amongst the hominids. So tools are only 1 hour old. Okay, so widespread use of stone tools is about 11 p.m. The first cities happened 11:59:35 p.m. So 25 seconds ago. The alphabet is about 9 seconds old. The Trojan War is about happened 7 seconds ago. The birth of Buddha was 5 seconds ago. Archimedean physics, the Roman Empire, happened about 4 seconds ago. The Roman Empire fell about 3 seconds ago. The Crusades were about 2 seconds ago, and the Renaissance was about 1 second ago. And the Renaissance is, of course, the origin of at least sort of the Western conception of what science looks like. So it's kind of remarkable that, at least in terms of sort of the Western model for how to do science, it's only about a second old, and so, in terms of placing yourself in the life of the universe, it's really only in the last second of the cosmic calendar that we can be asking the sorts of questions, the sorts of, scientific worldview driven questions that we've been talking about, only for about 1 second. So it's pretty remarkable, and we're pretty privileged to be living when we're living. Okay, so that's your place in time, but what about your place in space? So once again, because the numbers get incredibly big incredibly quickly, we need to come up with a mode for cheating. Okay, and so the cheat in this case takes advantage of Einstein's greatest contribution amongst many awesome contributions. So Einstein, through this burst of genius, came up with a special theory of relativity, which says that the speed of light is this cosmic speed limit. Nothing can go faster than the speed of light, 300,000 kilometers a second. So If Einstein is right, this is an absolutely fundamental limit on how fast something can go. So it's edifying to think about how the speed of light compares with the speed of things that we can put together. So the fastest thing that humanity has ever produced is the Voyager 2 space probe. This goes 60,000 kilometers an hour. This thing was launched in 1977, and he participated in this magnificent exploration of the outer solar system. And just last year, the Voyager space probe, launched in 1977, hit this thing called the heliopause, the outer boundary of our solar system, where people argue the solar system transitions into interstellar space. So the fastest thing humanity has produced, okay, launched in 1977, just last year in 2019, reached the edge of the solar system. So let's try and wrap our heads around our position in space using this trick. Okay, so moving at the speed of Voyager 2, it takes 13 minutes to cross the Earth. It takes 12 years to get to Pluto. It would take 80,000 years to get to the nearest star if Voyager 2 happened to be aimed at the nearest star, which of course it wasn't. And it would take 41 billion years to get to the Andromeda galaxy, the nearest big galaxy that resembles our own. 41 billion years. As I told you at the beginning of this talk, the universe is only 13.8 billion years old. So, it would take several lifetimes of the universe at present to get to the nearest big galaxy. Let's compare that to how fast it would take to do these things if you were moving at the speed of light. So you could get to you could cross the Earth in 0.04 seconds. You could get to Pluto in 6 hours. You get to the nearest star in 4.3 years, and you could get to the Andromeda galaxy in about 2 million years. So you can see that light goes unbelievably fast. And so this allows us to have our trick, okay, which is that we cannot deal with these enormous numbers. The distance to the nearest star is about 40 trillion kilometers. 40 trillion is a huge number. Like I was already telling you that 13.8 billion gives me angst, right? 40 trillion gives me way more angst. So the trick is you don't measure distance in terms of familiar units like the kilometer. Instead, what you do is you measure distance in terms of how far light can travel in 1 year. Okay, so that's what the light year is. Okay, it's a unit of distance. It's how far light can travel in 1 year, and it's about 10 trillion kilometers. So the nearest star is 4.3 light years away. So on that basis, okay, we can start to kind of position ourselves in this Milky Way thing that I was describing earlier. So the Milky Way is a frisbee-like structure. So it's flat. We are not located in the center of this big frisbee-like structure. Instead, we are located about 28,000 light years from the center. So this yellow arrow shows you in this kind of schematic picture of a different galaxy where we would be located. Okay, so 28,000 years from the center of this galaxy. And we are sharing this, gigantic frisbee in space with 100 billion other stars. So this is a picture, okay, of what you would see if you, went out on a beautiful dark night, far from city lights, and you looked up. What you would see would be this band of luminous cloud-like things that are stretched out in a line across the heavens, and that's the Milky Way. And so, when the ancients named the Milky Way, they were referring to this, cloud-like band, but what they were naming is our own galaxy. So our galaxy is named the Milky Way galaxy. And we, share this thing with about 100 billion other stars, and we're rotating around the center of it every 300 million years or so. But, and this is an important point, When you look at this beautiful picture, and you think, oh man, how amazing that this thing is so huge, and there are these 100 billion other stars, and here they look completely crammed together, and yet the distances between these stars are tens of trillions of kilometers, takes at the speed of light years to go from one star to the next, and yet here they look all crammed together. And your mind wants to explode with the beauty of this thing. The thing that should really make your mind explode is that what you see is just a tiny fraction of what's out there. Okay, so another magnificent discovery that's happened over the course of in this case, like the last 25 years, is this understanding that the universe is dominated by these things called dark energy and dark matter, which we just don't have the foggiest clue about. And 97% of what's out there is dark matter and dark energy, neither of which we could directly see. And the best we can come up with is ways of describing where this mysterious stuff that we don't understand is located, so how it's distributed. So we know that even though our universe is big, it's actually embedded within a much bigger dark matter halo, roughly spherical, that is much larger than the physical size of our galaxy. And we just can't see this stuff. We can only detect it indirectly by the way it bends the orbits of things through its gravity, and by the way it can bend light through another one of Einstein's massive contributions, which showed that gravity bends the motion of light as it passes through space. So the universe is dominated by dark matter and dark energy, neither of which we understand, both of which we're pretty sure is out there. So you should be thinking really in terms of dark matter. If you could have dark matter eyes, what you would see is that it dominates the universe, but it's not spread uniformly throughout space. So what this shows is the distribution of nearby galaxies in space. So this is from a survey known as the Sloan Digital Sky Survey, and where this telescope worked out the distances and positions to a bunch of nearby galaxies. So these things are, cosmically speaking, not very far away from us at all. Yet, in terms of familiar distances, they're incredibly far away. They're tens of millions of light years away. And the awesome thing that's emerged is that the galaxies themselves are distributed throughout the universe in this sort of a sponge-like structure. And the nature of this, why the sponge-like structure with these sheets and streams and filaments looks the way it is because of the mutual tug of the galaxies against each other. And in order to describe these shapes and predict the shapes that you see here, you need to do this in the context of a universe dominated by dark matter and dark energy. So these pieces fit together pretty nicely. Okay, so why should you believe anything I've just said? I've stood up here, and particularly if you kind of try and parse the stuff I just said, I painted a picture, for how astronomers, understand, the basic properties of the universe. And the remarkable thing is, near the end, I said, well, hang on, most of the stuff that's out there is actually invisible. And so I think that if you, have more than two neurons to rub together, you should be skeptical about people who, point to stuff without giving you evidence for it. And in particular, pointing to invisible stuff, because throughout the course of history, people have pointed to the existence of invisible stuff to explain physical phenomena, and they've always been proved wrong. Okay, so remember that we were supposed to be living in the center of the universe, and the stars were attached to these crystalline spheres that were being propelled by angels. That was wrong. If you want to move forward a little bit, the light itself was supposed to be traveling through this thing called the ether. So light is a wave, and waves need a medium in which to propagate. Waves in the ocean, basically there's water in the ocean that is basically the way gives the waves something to move within. So what does light move within? Okay, so there was this concept of this thing called the ether, and it turns out that the ether doesn't exist. Okay, so smug scientists telling you about stuff existing and later being proved wrong is actually a thing, and so you should be skeptical. But I'm going to tell you that we have a lot of evidence for this stuff, and furthermore, if you're an astronomer, you can collect special evidence that sadly, my other colleagues, my chemist colleagues, my material science physicist colleagues can't turn to. And so that's why I think we can get away with this, okay? And that's because we have figured out how to build time machines. So I love telescopes. I'm in my basement, and in that room over there, I've got like 8 telescopes. In my living room upstairs, I've got like another 9 or 10 telescopes. I freaking just love telescopes. And I love telescopes for many reasons. And one reason is because, of course, they can let you see things that are far away like they were near. But also, and this is where I think, a spirited astronomer really gets into telescopes, I love telescopes because they're time machines. So what do I mean by that? Okay, so what I mean by that is that light travels at a finite speed, and light is the way information gets carried through the universe. Now, another thing, we're super lucky to be living in an era where, just a couple of years ago, there was a discovery of gravity waves. So there's another way of communicating information over these vast distances, and that's going to be huge over the course of the next couple hundred years. I hope, we will learn, as much with gravity wave telescopes as we've learned from telescopes that use light, but that's pretty far away. So for now, we're dealing with light. And light travels at the speed of light, which is hugely fast but finite. And actually, so do gravity waves also travel at the speed of light. Okay, so why is this so important? Well, the reason it's so important is because the finite speed of light means that when you see something, you're not seeing it the way it is now, you're seeing it the way it was when it emitted that light. So for example, the sun is it took 8 minutes, okay, for the light emitted by the sun to get into your eyes. So you're not seeing the sun the way it is now when you look at the sun, which you shouldn't do because you burn out your retinas. But anyway, you're seeing the sun the way it was 8 minutes ago. Okay, so when you look at Pluto, you're not seeing Pluto, the way it is now. You're seeing Pluto the way it was like 12 hours ago. When you look at the nearest star, you're not seeing the nearest star the way it is now. You're seeing that star the way it was about 4 years ago. When you look at the nearest galaxy, the Andromeda galaxy, you're not seeing the Andromeda galaxy the way it is now. You're seeing it the way it was about 2 million years ago. So that's the trick, okay, is that the further out in the universe you look, the further back in time you see. So that's the nature of the time machine. So it's a special time machine. It's not like the TARDIS, where you can just take off and go anywhere or anywhere. The way this thing works is that you can only see the universe back in time. You can't go forward in time, but you can go backwards in time, and you can only go backwards in time somewhere else. So you can't go back in time where you are now. But anyway, it's awesome, okay, because it means that by building telescopes, you can look further and further back in time. So as you could see from my earlier ranting, I love dinosaurs. But I feel sorry for the poor paleontologists who have to study dinosaurs by going to museums and looking at fossils. If you're an astronomer and you want to see, the things that you study, like these galaxies and these stars, the way they were in the past, you just build a bigger telescope and you can see them the way they were in the past. So with the Hubble Space Telescope, we can see stuff about 12 billion light years away. Okay, so on our cosmic calendar, we can see stuff with the Hubble Space Telescope as it was in February, which is amazing, given that our solar system formed in May. So, we're able to see with our own eyes stuff in the universe billions of years before our sun even formed. So here are some fairly typical nearby galaxies, okay? They have these beautiful spiral forms, as I showed you earlier. There are other galaxies that look like these little blobs at the bottom, elliptical galaxies. And these things are being seen in the month of December. They're like, 60 million years, light years away. So we're seeing these things as they looked at about the time dinosaurs went extinct. And yet, these are cosmically speaking very nearby. So I made the point earlier, okay, that 97% of the universe is made up of stuff that we know not the first thing about. Another point worth making is that even amongst the 3% of stuff we think we know something about, we don't know very much stuff about that either. Okay, so let me tell you a little story. A colleague of mine at Yale and I got together with another colleague at Harvard, and we built this crazy telescope. Okay, so this is the Dragonfly telephoto array. That's me at the top right, assembling the prototype. Here's a bit of math, which is boring, except to make the point that as you take more and more of these lenses, which we strung together to make our fancy telescope, you get a bigger and bigger telescope. So you can continue this trick. Here's happy grad students with our fancy telescope. Here it is with 10 lenses. Here's 24 lenses. And right now this thing, the Dragonfly telephoto array, has got 48 lenses, and it's the largest all lens telescope in existence. So with this thing, with heavy reliance, I might add, on made in Canada technologies, we have made a series of really remarkable discoveries, including, finding a whole new class of galaxies, so-called ultra diffuse galaxies that are made almost entirely of dark matter, and almost identical looking ultra diffuse galaxies that have almost no dark matter, none of which was predicted. Okay, so and the only reason I'm telling you this is to make one point, which is that when it comes to the universe, we are clueless, and that is awesome, because it means that it's actually easy to make discoveries in astronomy. It's such an exciting subject to be working in. If you happen to be a kid thinking about what to do, what's the trajectory of my life? I think you should seriously think about astrophysics, because honestly, it's not that hard to make really cool discoveries. Whereas I think in some other sciences, it actually is pretty hard. We know a lot more about some things than we do about the universe. So it's easy, okay, for a couple of random idiot astronomers to put together a cool telescope and discover some new types of galaxies. But to understand things about them, that's where you need to turn to these really incredible facilities like the Hubble Space Telescope that let you take these things that you can see today and let you see them when they're far away, and then you can see how they evolve, basically by looking before your very eyes as things change with time. So that's the trick, the magic of astrophysics that we can pull off that the other sciences can't. So with the Hubble Space Telescope, we can look back in time. Okay, these objects are seen in May through August, and what we see is these galaxies that I just showed you earlier assembling before your very eyes. So these beautiful spiral and elliptical galaxies that look so symmetrical and smooth today, when you look back at them as they're assembling, they look like train wrecks. Okay, so this is the evolution of galaxies witnessed before your very eyes, just by looking at these things as they, form from the Big Bang, and then they crash together, kind of like train wrecks, and they assemble themselves into bigger galaxies that look like the ones we see today. So you can put this all together in this sort of a picture by working with colleagues who do theory, okay? Because you can't see dark matter, but they can stick dark matter in their computers, and when they do, they can crash these galaxies together in their computers, and what emerges is this picture that ties together the properties of the individual galaxies and their distribution in space. So when this thing, if you notice at the bottom left there, it gives you a clock since the Big Bang. When this thing gets to about 3 billion years, what you're going to see is a spectacular phenomenon that was not predicted until my colleagues and I, showed about 15 years ago that it had to be happening. And that is that in space, stuff blows up. So I, as you've inferred, am a big kid. And so when we discovered by finding this tremendous excess of evolved massive galaxies in the distant universe, and my theory colleagues said, well, hang on, the only way we can explain this is by having this process, which now is called feedback, but really should be called galaxies blowing up, I became incredibly happy. Okay, and that's the way discoveries happen. In astronomy, is typically it's a subject that's driven by observation. We build bigger and bigger and more powerful telescopes. We discover amazing new phenomena, and then we can turn to our colleagues who work in theory to try and understand what's going on. And so, and they do a pretty good job too, okay, by sticking together the elements that I've described in their computers. They can predict the existence of galaxies that look very similar to the ones that are actually observed. Okay, great. So we can do this with the Hubble Space Telescope, and we can get back to February if we try unbelievably hard. So are we going to be happy with February? Of course not. Okay, if you look at this picture, which is the Hubble Ultra Deep Field, and it represents humanity's deepest look out into space at the sorts of wavelengths you can see with your eye. So not fancy gamma rays or radio telescopes or anything, just visible light. This is what you get. Okay, and so this is just a tiny, tiny little portion of space. It's about the size of a dime held at arm's length in space, and this is what you get if you expose with the Hubble Space Telescopes for weeks of time. And the objects that you see here get out to about February, and every single one of these dots, with the exception of only maybe 6 or 7 objects on this image, are galaxies and not stars. So we're seeing out into the depths of space, but we are not getting to the point where we can see the first stars and galaxies. Okay, to do that, we would have to go further. February is not good enough. We need to go to early January. And so what is the plan there? So the plan there is this thing. So this is something called the James Webb Space Telescope. It is sitting disassembled in a warehouse in California, being tested and being prepared for launch. And prior to the coronavirus, the plan was to launch this thing in March of 2021, like 20 years late, because this is incredibly hard to build. It's much larger than Hubble. It's so big, it has to be folded up like an accordion to fit into the biggest rocket we could launch it in. And then instead of being in orbit around the Earth, it gets launched to beyond the moon. So this is an unbelievably challenging project that I've been involved in for like 15 years. And by no means have I been involved in this thing longer than many, many other of my colleagues. So it's an $8 billion mission. And it's going to be absolutely spectacular. So to explain why it's spectacular, let me try and show a movie. This is my colleague, Amber Strawn. who will explain to you why this thing is going to be as awesome as it's going to be.
The Hubble Space Telescope has shown us some amazing views of the universe. How will the Webb telescope improve on that?
Well, there's no doubt that the Hubble Space Telescope has completely revolutionized our understanding of the universe. But there are some things that Hubble just wasn't designed to do. So the Hubble is primarily an optical telescope. And one of the primary differences between Hubble and the James Webb Space Telescope is that Webb will see the universe in infrared light. And so by looking at the universe in infrared light, it will allow us to see back into the early universe, see some of the first stars and galaxies that formed. It will allow us to see down into the dusty clouds where stars are being born. So lots of different things that we'll be able to see with the Webb that Hubble can't quite see right now.
Okay, so I happen to be on the committee, or up until a year ago, I was on the committee that basically was overseeing the progress on this thing, and I was Canada's representative on it. So as a result, I get lots of sneaky pictures of this thing being assembled. So here it is being assembled for the first time in the clean room, and so you can see how huge it is. It's the Hubble Space Telescope has an aperture. The size of its mirror is 2.4 meters. This has an aperture of about 6.5 meters. Its mirrors are coated in gold because, as Amber just told you, its purpose is to study the universe in infrared light, which is appropriate to trying to study the most distant objects in the universe. Here it is folded up like a accordion, or I guess a transformer would be a cooler way of describing it. It is being put into the world's largest vacuum chamber, where it is being rattled around and shaken to make sure that it works before it gets loaded into a special airliner for transportation to California, where it is undergoing further testing, which is where it is now. And when this thing is put together, what it's going to do is allow you to see the universe to such faint levels, it should be capable of seeing the first collections of stars that formed in the universe. So this is a simulation showing you the Hubble deep field at the top, and in the bottom, what is predicted to be seen with the James Webb Space Telescope, and the lots of little dots in the bottom that you can see are the predicted sources of the light that set off a chain of events that ultimately led to the complicated universe you see now. Now, this simulation, is the product of thousands of supercomputing hours and, literally hundreds of the smartest people on the planet. And do I think this is what we're going to find? I do not. Okay, what I think we're going to find is that the universe is going to be way weirder and way more surprising than anything that we can think of now. And I just cannot wait for this thing to get launched, because 6 months later, when this thing gets out to beyond the moon and it becomes cooled, and we start taking pictures of stuff in the distant universe, what we see is going to be so far beyond what we can predict, it will just blow our minds away. So only like 2 years from now, hold on to your hats, because the James Webb Space Telescope is going to change everything. And who gets the credit for this? Well, I think you do. Okay, thank you. Because what I didn't mention earlier, but which is important to mention now, is that you helped pay for this. Okay, Canada is a partner in this, most ambitious space mission that humanity has ever embarked upon. So unlike with Hubble, where we kind of got a free ride, in this case, Canada actually built one of the 4 instruments, and we're a central partner in the success of this thing. And my participation in this has been made possible by your generosity and your willingness to support the sorts of science that we're doing at the University of Toronto and in the Department of Astronomy and Astrophysics and at the Dunlap Institute. So from the bottom of my heart, I would just like to say thank you, and I'll stop there. Thanks a lot.